Hello, everybody. My name is Eric D. Johnson, also known by BrightShine, right here in the city of Memphis in the county of Shelby State, Tennessee. Today's date, Sunday afternoon, September the 21st, 2025, time, 2:30 p.m. First, I thank my family, my support for the cheering girl support. I'll continue to keep myself employed in the Memphis tri-state area. Continue to further my education by studying business administration, contract, and marketing. At this present time, I took a break and going to school. But in the future, I will continue to further my education and continue to work toward earning my social degree in business administration, contract, and marketing, as well as other degrees. Now, I'm going to start my Facebook Live. Hello, everybody. My name is Eric D. Johnson, also known by BrightShine, right here in the city of Memphis, in the county of Shelby State, Tennessee. Today's date, Sunday afternoon, September the 21st, 2025, time, 2:31 p.m. First, say thank you to my family, my support, for continue to continue to keep myself employed in the Memphis tri-state area and continue to further my education by studying business administration, contract, and marketing. At the present time, I took a break and going to school. In the future, I'm going to go back to school. And I'm going to continue to work toward my social degree in business administration, contract, and marketing, as well as other degrees. Now, first, I want to say thank you, my Lord and Savior Jesus Christ, Son of God, for blessing me to see another day and to be able to say thank you, Jesus. And I want to continue to pray to my Lord and Savior Jesus Christ, Son of God, for all the blessings and the guidance He provides myself as well as all of us with, as well as continue to pray about these natural disasters, and because they get reported each and every day, and there's not just one kind or type of natural disaster. There are varieties of natural disasters. There are disasters that happen naturally on this earth, on this globe, on this planet. And continue to pray. And continue to pray about wars that are being fought all over the world. And continue to pray for peace. Now, going to continue focusing on prehistoric religion and traditional ancient African religion indefinitely. And continue to remember that the library has extensive amounts of material available for your assistance, and you can refer to the library, which I recommend, and also not just prehistoric religion, traditional ancient African religion, but also remember in the process of focusing on those subjects, don't overlook mathematics. Don't overlook mathematics. Okay. So like I said, we're going to be focusing on prehistoric religion / traditional ancient African religion, indefinite, and also mathematics, because mathematics is in all the fields of science, branches of science, and those branches of science are the areas that the scientists are utilizing in our focus on prehistoric religion and traditional ancient African religion. Now, that's a very important thing. Mathematics is important. All right, let me see. Okay. Let's see. All right, let me see. Now, Continue to focus on prehistoric religion / traditional / ancient African religion. And you know, there are books in the library on prehistoric religion and traditional ancient African religion. Books in the library. Prehistoric religion is the religious practice of prehistoric cultures. Prehistoric religion. Prehistory. The period before written records makes up the bulk of human experience. That's a very profound statement. When you talk about prehistoric, there's a lot of dinosaurs and there are a lot of various forms of life. But when you talk about prehistory, we're talking about human experience. Over 99% of human experience occurred during the Paleolithic period alone. And just click over there, right? Paleolithic, also called the Old Stone Age, is a period in human prehistory that is distinguished by the original development of stone tools, and which represents almost the entire period of human prehistoric technology. It extends from the earliest known use of stone tools by hominins 3.3 million years ago to the end of the Pleistocene. So, when we're talking about this Paleolithic age in Europe, preceded the Mesolithic age, although the date of the transition varies geographically by several thousand years, during the Paleolithic age, hominins grouped together in small societies such as bands and subsisted by gathering plants, fishing and hunting, or scavenging wild animals. The Paleolithic age is characterized by the use of knapped stone tools, although at the time humans also used wood and bone tools. Other organic commodities were adapted for use as tools, including leather and vegetable fibers. However, due to rapid decomposition, these have not survived to any great degree. Although, about 50,000 years ago, a marked increase in the diversity of artifacts occurred. In Africa, bone artifacts and the first art appeared in the archaeological record. The first evidence of human fishing is also noted from artifacts in places such as Blumbo's Cave in South Africa. Archaeologists classify artifacts of the last 50,000 years into many different categories, such as projectile points, engraving tools, sharp knife blades, and drilling and piercing tools. Humankind gradually evolved from early members of the genus Homo, such as Homo habilis, who used simple stone tools, into anatomically modern humans, as well as behaviorally modern humans by the Upper Paleolithic. During the end of the Paleolithic age, specifically the Middle or Upper Paleolithic age, humans began to produce the earliest works of art and to engage in religious or spiritual behavior such as burial and ritual. Conditions during the Paleolithic age went through a set of glacial and interglacial periods in which the climate periodically fluctuated between warm and cool temperatures. By 50,000 to 40,000 BP, the first humans set foot in Australia. By 45,000 BP, humans lived at 61 degrees north latitude in Europe. By 30,000 BP, Japan was reached. And by 27,000 BP, humans were present in Siberia, above the Arctic Circle. By the end of the Upper Paleolithic age, humans had crossed Beringia and expanded throughout the Americas continent. All right, the Paleolithic. Now, the fields of science, the branches of science. Formal science is a branch of science focused on abstract structures and knowledge derived from formal systems such as logic, mathematics, computer science, and statistics. These disciplines use deductive reasoning and abstract principles to create knowledge, relying on axioms and rules rather than empirical evidence or observations of the real world. Although they are a priori and lack direct empirical content, formal sciences are crucial for the empirical sciences, providing the fundamental frameworks and tools necessary for many quantitative and analytical fields. Now, this is coming from the artificial intelligence overview. Now, key characteristics. Formal systems. Formal sciences are built on formal systems, abstract structures with axioms and rules used to derive theorems. Deductive reasoning. They rely exclusively on deductive reasoning, moving from general principles to specific conclusions. A priori knowledge. Formal sciences are a priori disciplines, meaning their content and validity are independent of empirical experience or observation. Abstract nature. They deal with abstract concepts and structures, not with the contingent facts of the real world. Examples of formal sciences. Mathematics, the study of numbers, quantity, space, and structure. Logic, the study of correct reasoning and argumentation. Computer science, theoretical, the theoretical foundation of computation and algorithms. Statistics, the science of collecting, analyzing, and interpreting data. Information theory, the study of the quantification, storage, and communication of information. Systems theory, the study of complex systems and their emergent properties. Game theory, the study of strategic decision making in interactive situations. Linguistics theoretical, the study of formal aspects of language, such as syntax and semantics. Then you have the relationship to empirical sciences. Foundational role. Formal sciences provide the conceptual and quantitative frameworks that empirical sciences use to describe and understand the world, independent of empirical evidence. Unlike empirical sciences, which require experiments and observations, formal sciences derive their conclusions through pure logical deduction. The broad applicability, because their conclusions are based on necessity and pure reason. The findings of formal sciences apply across all domains and are essential for the development of natural and social sciences. Formal science. Natural science. Artificial intelligence overview. Natural science is an umbrella term for the academic disciplines that study the natural world through observation and experimentation. These fields use empirical evidence to understand, describe, and predict natural phenomena. Natural science is typically divided into two main branches: life science and physical science. The major branches of natural science. Life science, biology. This field investigates living organisms and their relationship with one another and the environment. Molecular biology studies life at the molecular and biochemical level. Cell biology focuses on the structure and function of the cell, the basic unit of all life. Genetics examines heredity, genes, and a variation of inherited characteristics. Ecology explores how organisms interact with their environments. Zoology, the study of animals. Botany, the study of plants. Microbiology, the study of microscopic organisms like bacteria and viruses. Physical science. This branch of science studies non-living systems and can be further subdivided. Physics, considered foundational to all other natural sciences. Physics investigates the fundamental constituents of the universe, such as matter, energy, motion, and force. Chemistry studies the composition, structure, properties, and reactions of matter at the atomic and molecular scale. Earth science, an all-encompassing term for sciences related to the planet Earth. Geology, the study of the Earth's solid structure. Minerals and how it changes over time. Meteorology focuses on Earth's atmosphere, weather, and climate. Oceanography investigates the oceans, including marine life, currents, and the geology of the seafloor. Astronomy studies celestial objects and phenomena that originate outside Earth's atmosphere. Key characteristics of natural science. Empirical evidence. Natural sciences rely on data and evidence gathered through observation and experimentation. Scientific method. A systematic approach to inquiry that involves formulating and testing hypotheses. Reproducibility. Scientific findings are expected to be reproducible, meaning other researchers can replicate the results. Interdisciplinary. While distinct, the boundaries between the natural sciences are not always sharp. Many fields, like environmental science, draw from multiple disciplines. Natural science versus social science. Natural science is distinct from social science, which seeks to understand human societies and relationships. However, some fields may overlap, such as environmental science, which considers the impact on human activities on the environment. Natural science. Now, remember, this is artificial intelligence overview. Social science refers to academic fields that systematically study human society, individual behavior, and social relationships. Key disciplines within social science include anthropology, sociology, psychology, political science, and economics. These fields use systematic research methods to understand and explain how individuals and groups function within their social, cultural, and economic environments with the goal of informing policies and promoting positive social change. What social science studies? Human behavior. It examines why people act the way they do, both as individuals and in groups. Social interactions. It looks at the relationships, behaviors, and connections between people. Societies and cultures. It investigates how societies and cultures are formed, develop, and function. Institutions. It analyzes institutions like governments, economies, and families to understand their role in society. Now you have major branches of social science. Anthropology, the study of humans, societies, and their cultures. Often across history. Right? Economics, the study of how people produce, distribute, and consume wealth. Political science, the study of government, political systems. Psychology, the study of the human mind and behavior. Sociology, the study of society, social groups, and the relationships between them. Other related disciplines. Other fields often considered part of social science include history, geography, communications, and linguistics. Popular purpose of social science. Understanding the world, to provide a deep understanding of complex human systems and global issues. Informing decisions, to help leaders and policymakers create better policies by providing insights into social dynamics. Promoting change, to equip people with the knowledge and skills to make a positive difference and drive social change. Developing skills, to foster skills in research, writing, communication, and critical thinking. social science. Mathematics is the science of structure, order, and relation, dealing with numbers, quantities, shapes, space, and change through logical reasoning and rigorous deduction. It's a fundamental tool in physical and life sciences, as well as technology evolving from practical pursuits like commerce and agriculture. Key areas within mathematics include number theory, algebra, geometry, calculus, and logic, with mathematicians finding patterns and establishing truth through axioms and definitions. What is mathematics? Core concepts. Mathematics studies numbers, quantities, shapes, space, and how they change. Logical foundation. It relies on logical reasoning, quantitative calculation, and the establishment of truth through rigorous proof from chosen axioms. Evolution. Mathematics has developed over thousands of years, evolving from practical needs into an increasingly abstract and idealized discipline. Key areas of mathematics. Number theory, the study of the properties and relationships of integers. Algebra uses symbols to represent unknown values and form equations to solve for them. Geometry focuses on shapes, sizes, positions, and properties of objects in space. Okay. Calculus involves derivatives and integrals to study rates of change and predict motion. Set theory deals with the foundations of numbers and logic. Mathematical logic studies the foundations of reasoning, proof, and truth used in formal systems. Why is mathematics important? Science and technology. It is an indispensable adjunct to the physical sciences and technologies. Life sciences plays a similar role in the quantitative aspects of the life sciences, such as the study of disease spread. Daily life, mathematical principles are used in countless everyday activities, from calculating the path of a fastball to understand the cooling of hot cocoa. Mathematics. See, I'm looking at it's still artificial intelligence overview. It's worded a little different on my tablet. Well, well, like I said, artificial intelligence. That's why I was looking at it. It was worded different, but it's artificial intelligence. Okay. Mathematics is a cornerstone of formal science, serving as the abstract language of patterns, structures, and relationships that underpins all quantitative science, including the natural sciences like physics and chemistry. Unlike empirical sciences that rely on observation, formal sciences like mathematics derive knowledge through logical deductions from axioms, a process that generates certain arguments but doesn't guarantee correspondence to physical reality. How mathematics functions in formal science. Foundation of knowledge. Again, how mathematics functions in form of science. Foundational knowledge. Mathematics provides the essential framework and tools for other forms of sciences such as logic and computer science, and indirectly supports natural sciences by providing models for their phenomena. Abstract structures. Mathematics deals with abstract concepts, numbers, and quantities rather than physical objects. It uses formal systems and axioms to build and organize knowledge in a systematic way. Logical deduction and proof. Mathematical knowledge is generated through logical deduction from fundamental premises called axioms. A proof in mathematics demonstrates that a result must necessarily follow from these premises. Then, of course, mathematics as a form of science. Mathematics as a form of science. Systematic enterprise. Mathematics is considered a form of science because it is a systematic endeavor that builds and organizes knowledge, often through the use of formal methods and machine checkable proofs. Focus on patterns. It is fundamental to study patterns, their description, and their explanation, which are crucial for analytical work in all fields. Independence from empirical testing. While empirical sciences are tested through observation and experimentation, mathematics is not, as its objects of study are abstract, and its truth is established through proof, not physical evidence. The relationship with other sciences. The queen of the sciences, due to its fundamental role, mathematics often called the queen of the sciences by mathematicians and thinkers like Carl Friedrich Gauss, reflecting its critical importance for other scientific disciplines. Tools for application. The abstract structures and principles of mathematics are used to represent real-world phenomena in physics, engineering, and other fields, creating contextual meaning and enabling predictions about the world. Okay. Let me see here. Now, this is one of the formal sciences, mathematical logic, because as you know, logic is one of the formal sciences, logic. So mathematical logic. Okay, so let me see here. Okay. Okay. Mathematics in natural science. Mathematics provide the essential language, tools, and models for natural scientists to describe, analyze, predict, and understand natural phenomena. From the microscopic world of quantum mechanics to the macroscopic scale of galaxies and ecosystems. It enables scientists to formulate theories, interpret data, identify patterns, and create formal frameworks that reveal the deep, often hidden mathematical structures governing the universe. As highlighted by Galileo's observation that the laws of nature are written in the language of mathematics. Okay, the key roles of mathematics in natural science. The language of nature. Mathematics offers a precise and universal language for expressing complex natural laws and phenomena, providing a foundational framework for physics, chemistry, and biology. Modeling and prediction. Scientists use mathematical models to simulate natural processes from disease spread and population dynamics in ecology to the behavior of particles in quantum physics. These models help predict future states of systems and test hypotheses. Data interpretation. Mathematical methods are crucial for processing and interpreting experimental data, allowing scientists to identify significant patterns and draw meaningful conclusions from observations. Discovery. Mathematical frameworks developed for theoretical purposes can often anticipate physical phenomena. For example, the geometric work that preceded Einstein's theory of relativity involved mathematical concepts that were later found to describe the physical world. Understanding fundamental law. Understanding fundamental laws. Theoretical physics relies heavily on mathematics to explore fundamental laws like quantum mechanics and relativity, with mathematical structures pointing towards deeper understandings of the universe. Examples of mathematics in action. Physics. Equations like E equals MC squared and Schrodinger's equation are mathematical expressions of fundamental physical laws. General relativity, describing gravity, was enabled by earlier mathematical work on differential geometry. Ecology. The Lotka-Volterra equation models the interactions between predator and prey populations, helping ecologists understand ecosystem stability. Chemistry. Mathematical models are used to study how laws of physics affect elements, leading to the formation and interaction of molecules from water to polymers. Crystallography. Group theory, a branch of higher mathematics, is used in the study of mineralogy and crystal structures. Biology. There are efforts to use knot theory to topologically classify different proteins. And of course, you know I'm reading from Artificial Intelligence Overview. Now let's address this book that was written, or this article. Let me click on the unreasonable effectiveness of mathematics in the natural sciences. The unreasonable effectiveness of mathematics in the natural sciences is a 1960 article written by the physicist Eugene Wigner, published in Communication in Pure and Applied Mathematics. In it, Wigner observes that in theoretical physics, mathematical structure often points the way to further advances in that theory and to empirical predictions. Mathematical theories often have predictive power in describing nature. Okay. All right, this is the article. The unreasonable effectiveness of mathematics in the natural sciences. Okay. Now I'm reading from this artificial intelligence overview. Mathematics and life sciences. A field often called mathematical biology uses quantitative tools and mathematical models to understand biological systems, from cells and genes to entire ecosystems. It helps researchers to measure, describe, and predict biological phenomena like disease spread, population changes, gene expression, and the function of physiological systems. Key mathematical concepts used include statistics, calculus, differential equations, dynamical systems, and network science. Now, you have applications in the life sciences, ecology and evolution, modeling population dynamics like the Lotka-Volterra equations for predator-prey interactions, and understanding evolutionary benefits. Epidemiology, tracking and predicting the spread of diseases within populations. Genetics and molecular biology, analyzing gene regulatory networks and the impact of mutations. Physiology, creating models of systems like the heart to simulate blood flow and test drug effects. Bioinformatics, analyzing large biological data sets to extract meaningful information. Key mathematical tools, mathematical models, equations, and formulas used to represent and understand complex biological systems. Biostatistics, statistical analysis to interpret biological data and draw conclusions. Differential equations, tools to describe how biological systems change over time. Dynamical systems, analyze the time-dependent behavior of biological systems, including chaotic behavior. Stochastic and probabilistic modeling, describing systems with inherent randomness and uncertainty. Why it matters. Predictive power transforms biology from a purely descriptive science into a predictive one. Understanding complexity simplifies complex biological systems into manageable models that reveal key insights. Experimental design allows for in silico computer-based experiments that can reduce the need for expensive or harmful animal testing. Interdisciplinary collaboration fosters collaboration between mathematicians, biologists, and other scientists to address critical challenges.
Now, mathematics and biology, or mathematical biology. I'm reading the artificial intelligence overview. Mathematical biology is an interdisciplinary field that applies mathematical theories and methods to model and understand biological systems, from genetics and disease spread to evolution and ecology. It involves constructing mathematical models to generate novel predictions, test complex biological hypotheses, and ultimately accelerate scientific breakthroughs that might otherwise require extensive experimentation. What it is: a field of study. Mathematical biology integrates mathematical concepts with biological science to create new insights into living systems. A set of tools. It uses various mathematical tools such as probability, calculus, and computational methods to analyze biological processes. How it works: modeling biomathematicians develop theoretical models to represent biological phenomena. Testing and predictions. These models help test assumptions that are hard to assess experimentally and generate predictions that guide future research. Efficiency. By allowing for simulation and analysis, mathematical biology can reduce the time and resources needed for biological research, leading to faster breakthroughs. Examples of applications: epidemiology, modeling the spread of infectious diseases; genetics, understanding genetic inheritance patterns and the likelihood of specific traits appearing; ecology, studying the interactions between different species within an ecosystem; biotechnology and healthcare, revolutionizing various aspects of these industries. Why it's important? It offers a powerful way to explore biological systems in a quantitative and precise manner. It can reveal hidden patterns and relationships within complex biological data that are not apparent through experimentation alone. Mathematical and theoretical biology. Okay, the artificial intelligence overview, mathematics and physical science. Mathematics provides the essential language and framework for the physical sciences, enabling scientists to describe, quantify, and predict natural phenomena through equations and models. It forms the basis for fields like physics and engineering, using tools such as algebra, calculus, differential equations, and statistics to analyze data, solve problems, and develop theories about the universe. Role of mathematics in physical science. Descriptive language. Mathematical equations express physical laws precisely, offering a universal language to communicate and understand complex systems. Predictive power. Mathematical models allow scientists to make accurate predictions about how physical systems will behave, which is crucial for testing theories. Analytical tool. Techniques like calculus and statistics are vital for analyzing data, interpreting experimental results, and verifying scientific theories. Key mathematical concepts in physical science. Algebra. Essential for basic physics, solving equations, and manipulating formulas. Calculus. Necessary for understanding rates of change and accumulating quantities, which is fundamental to classical mechanics. Differential equations. Used to describe how systems change over time, vital in field theory and quantum mechanics. Linear algebra and vectors, crucial for representing physical quantities and their interactions, particularly in quantum mechanics. Probability and statistics, used to analyze data and understand inherent uncertainties in physical phenomena. Tensor analysis applies to advanced physics and the study of gravity. Complex numbers and Fourier series used in areas like wave phenomena and signal processing. Bridging mathematics and physical science. Mathematical physics. This specialized field develops mathematical methods for physics problems and applies them to new theories. Interdisciplinary learning. Many students in the physical sciences, particularly in physics, chemistry, and engineering, take courses in mathematical methods to gain the specific skills needed to solve real-world problems. Inspiration. The relationship is symbiotic, with mathematics providing the tools for physics, and physics inspiring mathematicians to develop new mathematical concepts. Now there's this book that was published. It's a textbook, and the title of the book is Mathematical Methods in the Physical Sciences. Okay. Okay. Mathematics in the physical sciences. Language of science, mathematics provide precise language to describe. You see many algebra, quantum mechanics. Okay. This is artificial intelligence overview. Mathematics in physical science. Oh, okay. Mathematics provides the essential language and tools to express, analyze, and predict natural phenomena in the physical sciences. Fields like calculus, algebra, and statistics enable scientists to model complex systems, solve physical equations, and verify theories. Common examples of mathematical applications include using differential equations to describe motion, linear algebra for quantum mechanics, and vector analysis for electromagnetism. Why math is essential for physical science. Language of science. Mathematics provides precise and universal language to describe the fundamental laws of nature and the behavior of physical systems. Modeling and predictions. Mathematical models allow scientists to represent complex physical phenomena and make accurate predictions about their future behavior. Analysis and verification. Mathematical techniques are used to analyze data, interpret experimental results, and verify scientific theories. Problem solving. Math skills are crucial for students and professors to solve physical problems from basic mechanics to advanced quantum physics. Key mathematical concepts in physical science. Algebra, used for basic physics problems and to manipulate variables in equations. Calculus, essential for understanding rates of change, motion, and energy, forming the basis of classical mechanics. Differential equations, used to describe how physical systems change over time and in space, such as in wave and heat conducted problems. Linear algebra, indispensable in quantum mechanics for describing states and transformations of systems. Vector and tensor analysis, used in fields like electromagnetism and fluid mechanics to handle quantities with both magnitude and direction, probability and statistics, employed in analyzing experimental data and dealing with uncertainties in physical measurements. How math and physics intersect. Mathematical physics. This specialized field develops mathematical methods specifically for application to physics problems and formulates new physical theories using those methods. Inspiration. Physics inspires mathematicians to develop new mathematical tools and, and concepts, creating a symbiotic relationship between the two fields. Now, what is book at? Okay. Like I said, there's this textbook titled Mathematical Methods in the Physical Sciences. Just give a little background on this. All right. Mathematical Methods in the Physical Science is a 1966 textbook by mathematician Mary L. Boas, intended to develop skills in mathematical problem solving needed for junior to senior graduate courses in engineering, physics, and chemistry. The book provides a comprehensive survey of analytical techniques and provides careful statements of important theorems while omitting most detailed proofs. Each section contains a large number of problems with selected answers. Numerical computational approaches using computers are outside the scope of the book. The book, now in its third edition, was still widely used in university classrooms as of 1999. It is frequently cited in other textbooks and scientific papers. So like I said, the title of this book is it's a textbook, Mathematical Methods in the Physical Sciences. almost forgot. Now, let me say that. Physical science is a natural science that studies non-living systems covering fields like chemistry, physics, astronomy, and the earth sciences, including geology and meteorology, to understand the fundamental nature of matter, energy, space, and time. These disciplines aim to explain the behavior of the inorganic world, focusing on its physical and chemical properties and how these elements interact and change, independent of living organisms. Key characteristics focus on the non-living. Physical science is distinct from life science, which focus on living organisms, study of matter and energy. The core of physical science is understanding the properties, constituents, and behavior of both matter and energy. Broad and interdisciplinary, it encompasses a wide range of subjects, providing the foundation of understanding for many scientific and technological applications. The main branches. The major disciplines within the physical science include physics, the study of matter, its fundamental constituents, its motion, and its behavior through space and time, along with the related concepts of energy and force. Chemistry, the study of the properties, composition, and structure of matter, as well as the changes that matter undergoes. Earth sciences, a group of science that study the non-living components of Earth, such as geology, the study of the Earth's structure and the processes that shape it. Meteorology, the study of the atmosphere and its phenomena, including weather. Astronomy, the study of celestial objects in the universe beyond Earth. Now, applications. Understanding physical science is crucial for many technologies we use daily, including computers, cell phones, and appliances, which are built upon principles from physics and chemistry. Now, this is the outline of physical science. Now, mathematical physics. Now, when we talk about the physical science, one of the physical science is earth science or geoscience. It's a diverse field of natural science that studies the solid earth, its water, its atmosphere, and its living organisms, as well as the dynamic process and interactions between these systems. It aims to understand the earth's past, present, and future, encompassing disciplines such as geology, oceanography, meteorology, and environmental science to address issues like natural resources, climate change, and geological hazards. Well, earth science studies. Earth science examines the planet's four main spheres and the complex systems that connect them. Geosphere, the solid earth, including rocks, minerals, soils, and the earth's interior structure. Hydrosphere, or cryosphere, all the water on earth, such as ocean, lakes, and rivers, as well as ice and snow. Atmosphere, the air that surrounds the earth, influencing weather, climate, and atmospheric chemistry. Biosphere, the sum of all life on earth, including ecosystems, and the interaction between living organisms. Key branches of earth science. Earth science is an interdisciplinary field with many specialized branches. Geology, the study of the solid earth, its rocks, minerals, and the forces that shape it. Oceanography, the study of the oceans and their physical, chemical, and biological aspects. Meteorology, climatology, the study of weather, climate, and the processes of the atmosphere. Geochemistry, the study of the chemical composition of the earth and its various components. Environmental science, the study of the earth's environment and the effects of human activity on it. Geophysics, the application of physical principles to understand the earth's physical properties and process. Importance of earth science. Understanding earth science is crucial for several reasons. Natural hazard management. Studying earthquakes, volcanoes, floods, and landslides helps to predict and mitigate their impacts. Resource management. Geoscience provides knowledge about the location and sustainable use of natural resources, including water, minerals, and energy sources. Environmental stewardship. It helps scientists understand climate change, ocean health, and the intricate balance of Earth's ecosystem. Planetary evolution. Excuse me. By studying Earth's history, scientists gain insights into how planets form and evolve, which is essential for understanding our own planet. Earth science. Mathematics in the earth sciences. Mathematics in the earth sciences, a field called geomathematics, is crucial for understanding, modeling, and predicting complex earth systems like climate change, geological formation, and natural resource distribution. Key mathematical tools include calculus, linear algebra, differential equations, statistics, and computer programming, which enable quantitative analysis, data interpretation, and the development of predictive models for environmental processes. Applications of mathematics in earth sciences. Geological modeling. Math is used to describe and model earth dynamic processes such as the evolution of coastlines or the carbon cycle using fundamental laws of physics and chemistry. Quantitative analysis. It allows for statistical analysis of geological data, the development of quantitative prediction models, and the interpretation of spatially referenced data. Geophysical processes. Fields like geodynamics and seismology rely heavily on mathematical methods to understand Earth's movements and structure. Environmental science. Math is essential for analyzing and predicting environmental changes including atmospheric phenomena, ocean currents, and the biogeochemistry of ecosystems. Key mathematical concepts and techniques: calculus, a fundamental tool for understanding rates of change in accumulating processes in earth sciences. Linear algebra, used in modeling terrain, analyzing soil properties, and understanding the relationship between different geological factors. Differential equations, critical for representing and solving problems related to dynamic earth systems and complex processes. Statistics, essential for quantifying uncertainty, analyzing data variability, and establishing correlations within earth science data. Computer programming, used to implement mathematical models and analyze large data sets with tools like Python and MATLAB commonly employed. The role of geomathematics. Geomathematics is the interdisciplinary field that brings together mathematicians, statisticians, and earth scientists to solve complex problems. It recognizes that mathematical rigor and quantitative methods are vital for advancing the understanding of our planet. Geomathematics. Social science. Social science are a collection of academic disciplines focused on the systematic study of human society and the relationships among individuals and groups within it. Key disciplines include anthropology, economics, geography, history, political science, psychology, and sociology, all of which employ scientific research methods to understand human behavior, culture, and social institutions. Social science research provides insights and skills that help shape public policy, social reform, and the design of educational programs and marketing strategies. What social sciences study? Social sciences explore various aspects of human life and society, such as human behavior, understanding individual motivation, actions, and interactions, social structure, examining how societies are organized, including families, institutions, and governments. Cultural norms, investigating cultural practices, beliefs, and values. Social systems, analyzing economic, political, and other systems that shape society. Key disciplines. Major branches of social science include anthropology, the study of human origins, cultures, and societies; economics, the study of the production, distribution, and consumption of goods and services; geography, the study of the Earth's physical features, climate, and the relationship between people and their environment; history, the study and interpretation of past events in society; political science, the systematic study of political institutions and behavior; psychology, the study of the human mind, behavior, and its functions; sociology, the study of human lives, social interactions, societal structures, and changes; applications and impact. Social science research has practical applications in various sectors. Public policy informs decision making by leaders and governments to address societal issues like unemployment, inequality, and social change. Education shapes the design of educational programs and strategies to meet societal needs. Business and marketing provides insights for creating marketing strategies and understanding consumer behavior. Social reform offers a framework for understanding complex social dynamics to drive positive change. Social science. Now, when it comes to mathematics and social science mathematics involve using mathematical models, statistics, and data analysis to understand and explain human behavior, social relationships, and societal phenomena, with applications in fields like economics, sociology, political science, and psychology. Core mathematical concepts include calculus, linear algebra, probability, and various types of models like regression and game theory to simplify complex social processes and make predictions. This interdisciplinary field, often called computational social science, emphasizes quantitative methods for research and problem solving. Key areas of application: economics uses models such as the demand-supply model to understand market dynamics and forecast economic trends. Sociology employs network analysis and game theory to study social interaction, relationships, and coordination games. Political science applies mathematical models to describe voter behavior and analyze political process. Psychology uses mathematical and statistical models to study human behavior and cognitive processes. Mathematical concepts and tools: mathematical models, abstract representations of real-world social phenomena that simplify complex systems for analysis and understanding. Regression analysis, a statistical tool used to establish and quantify relationship between variables. Game theory, analyze strategic interactions among individuals or groups, such as in the coordination of collective action. Network analysis, used to map and understand social connections and structures. Calculus, essential for optimizing functions and understanding rates of change in societal and economic systems. Linear algebra provides tools for working with multiple variables and complex relationships within models. Probability and statistics, fundamental for data analysis, hypothesis testing, and understanding uncertainty in society, in social data. Now, why it matters: problem solving. Math provides a rigorous framework to solve complex problems in human society that might otherwise be difficult to analyze. Predictive power. Mathematical models can help forecast future trends in areas like economics, population behavior, and social change. Research rigor. Quantitative methods and mathematical tools provide a strong foundation for social science research, leading to more objective and evidence-based conclusions. Let me see. Now, mathematics in cognitive science. Mathematics in cognitive science serves two primary roles: building mathematical models of cognition and studying the cognitive basis of mathematics itself. Cognitive science uses mathematics like probability and statistics to model uncertainty and analyze data, algebra, and calculus, to represent dynamic systems and neural networks, and information theory to understand the information processing in the brain. Conversely, fields like numerical cognition investigate the neural and psychological foundations of how humans understand numbers and mathematical concepts, drawing on empirical research to understand the cognitive and biological process behind mathematical thinking. Mathematics as a tool for cognitive science. Modeling. Mathematics provide frameworks to create quantitative theories and models of cognitive processing such as decision making, perception, learning, and memory, probability, and statistics. Modeling. Mathematics provide frameworks to create quantitative theories and models of cognitive process such as decision making, perception, learning, and memory, probability, and statistics. These are crucial for modeling uncertainty, making predictions, and analyzing experimental data in cognitive psychology and neuroscience. Algebra and calculus, used to represent and manipulate complex multidimensional data like images and language, and to model dynamic systems like neural networks over time. Information theory helps to measure and model the amount of information processed by the brain, particularly in areas like communication and sensory perception. Machine learning. Techniques like linear algebra and signal processing are fundamental for building computational models that can learn and perform intelligent tasks. The study of mathematical cognition. Numerical cognition. This subfield explores the cognitive, developmental, and neural basis for numerical and mathematical abilities in humans. Cognitive foundations of mathematics. Researchers examine how fundamental cognitive mechanisms like image schemas, conceptual metaphors, and neural circuits contribute to the human ability to create and understand mathematics. Neural and biological roots. Evidence suggests shared ancient foundations for number and space between humans and other primates, with specific neurons in the parietal lobe responding to numerical quantities. Mathematical thinking. The capacity for mathematical reasoning is seen as a potential benchmark for what it means to think and understand it. It requires integrating mathematical theory with empirical cognitive science, applications and interconnections. Artificial intelligence, cognitive science principles and mathematical models derived from human cognition are applied to improve artificial intelligence systems. Education, insights from cognitive science can inform and improve mathematics education by understanding how abstract mathematical concepts are learned and processed in the brain. Interdisciplinary nature. Mathematics in cognitive science is highly interdisciplinary, involving cognitive psychology, neuroscience, linguistics, and computer science to achieve a holistic understanding of the mind. numerical cognition. Now, we're back over here on the Paleolithic. Now we over here on the Paleolithic. I let me see, Neptune, okay, right, okay. Was a time period floods away. Okay. Now we over. Okay, I know where we at. Paleography and climate. Time. deep time. Space time. Abiogenesis. The history of life. The timeline of life. Human evolution. the timeline of human evolution. Now, like I said, we over here on the Paleolithic. When you say the Paleolithic, the Old Stone Age. You got lower, middle, and upper Paleolithic. And Paleolithic, Old Stone Age. So let me scroll back down to Paleography and Climate. The Paleolithic overlaps with the Pleistocene epoch of geological time. Both ended 12,000 years ago. Although the Pleistocene started 2.6 million years ago, 700,000 years after the Paleolithic's start. This epoch experienced important geographic and climatic changes that affected human society. Now don't forget, when you're talking about the Paleolithic, you're not talking about anything other than human. It's talking about the Stone Age, when humans lived on this earth. That's what this Paleolithic is talking about. It's talking about humans. And when they made those stone tools, it's not talking about anything. When you talking about the Paleolithic, the only thing you talking about is humans making stone tools. And so let me read that again. Let me read that first statement about the Paleolithic, so you won't make sure we don't forget. We're not talking about the Pleistocene or the Pliocene. We're talking about the Paleolithic. The Paleolithic, also called the Old Stone Age, is a period in human prehistory that is distinguished by the original development of stone tools, and which represents almost the entire period of human prehistoric technology. It extends from the earliest known use of stone tools by hominins 3.3 million years ago to the end of the Pleistocene, 11,650 BP. All right, so let me scroll back down. We back on the paleography and climate, which is important. And this, okay, well, what I left off, years after the Paleolithic start. Okay, this epoch experienced important geographic and climatic change that affected human society. During the preceding Pliocene, the continents had continued to drift from possibly as far as 250 kilometers, 160 miles, from their present location to positions only 770 kilometers or 43 miles from their current location. South America became linked to North America through the Isthmus of Panama, bringing a nearly complete end to South America's distinctive marsupial fauna. The formation of the Isthmus had major consequences on global temperatures because warm equatorial ocean currents were cut off, and the cold Arctic and Antarctic waters lowered temperatures in the now isolated Atlantic Ocean. Most of Central America formed during the Pliocene to connect the continents of North and South America, allowing fauna from these continents to leave their native habitats and colonize new areas. Africa's collision with Asia created the Mediterranean, cutting off the remnants of the Tethys Ocean during the Pleistocene. The continents were essentially at their modern positions. The tectonic plates on which they sit have probably moved at most 100 kilometers or 62 miles from each other since the beginning of the period. Climates during the Pliocene became cooler and drier and seasonal, similar to modern climates. Ice sheets grew on Antarctica. The formation of an Arctic ice cap around 3 million years ago, a signal by an abrupt shift in oxygen isotope ratios in ice rafted cobbles in the North Atlantic and North Pacific Ocean beds. Mid-latitude glaciation probably began before the end of the epoch. The global cooling that occurred during the Pliocene may have spurred on the disappearance of forests and the spread of grasslands and savannas. The Pleistocene climate was characterized by repeated glacial cycles during which continental glaciers pushed to the 40th parallel in some places. 4 major glacial events have been identified, as well as many minor intervening events. A major event is a general glacial excursion termed a glacial. Glacials are separated by interglacials. During a glacial, the glacier experiences minor advances and retreats. The minor excursion is a stadial. Times between stadials are interstadials. Each glacial advance tied up huge volumes of water in continental ice sheets. 1,500 or 3,000 or 4,900 or 9,800 feet deep, resulting in temporary sea level drops of 330 feet or more over the entire surface of the earth. During interglacial time, drowned coastlands were common, mitigated by isostatic or other emerged motion of some reason. The effects of glaciation were global. Antarctica was ice-bound throughout the Pleistocene and the preceding Pliocene. The Andes were covered in the south by the Patagonian ice cap. There were glaciers in New Zealand and Tasmania. The decaying glaciers of Mount Kenya, Mount Kilimanjaro, and the Rwenzori Range in East and Central Africa were larger. Glaciers existed in the mountains of Ethiopia and to the west in the Atlas Mountains. in the northern hemisphere, many glaciers fused into one. The Cordilleran ice sheet covered the North American Northwest. The Laurentide covered the east. The Fennoscandian ice sheet covered northern Europe, including Great Britain. The Alpine ice sheet covered the Alps. Scattered domes stretched across Siberia and the Arctic shelf. The northern seas were frozen during the late Upper Paleolithic, latest Pleistocene. The Beringia land bridge between Asia and North America was blocked by ice, which may have prevented early Paleo-Indians, such as the Clovis culture, from directly crossing Beringia to reach the Americas. According to Marlinus, all through collected data, the Pleistocene's overall climate could be characterized as a continuous El Nino, with trade winds in the South Pacific weakening or heading east, warm air rising near Peru, warm water spreading from the West Pacific and the Indian Ocean to the East Pacific and other El Nino markers. The Paleolithic is often held to finish at the end of the Ice Age, the end of the Pleistocene epoch, and Earth's climate became warmer. This may have caused or contributed to the extinction of the Pleistocene megafauna, although it is also possible that the late Pleistocene extinctions were, at least in part, caused by other factors such as disease and overhunting by humans. New research suggests that the extinction of the woolly mammoth may have been caused by the combined effect of climatic change and human hunting. Scientists suggest that climate change during the end of the Pleistocene caused the mammoth's habitat to shrink, resulting in a drop in population. The small populations were then hunted out by Paleolithic humans. The global warming that occurred during the end of the Pleistocene and the beginning of the Holocene may have made it easier for humans to reach mammoth habitats that were previously frozen and inaccessible. Small populations of woolly mammoths survived on isolated Arctic islands, St. Paul Island and Wrangel Island, until 3700 BP and 1700 BP respectively. The Wrangel Island population became extinct around the same time the island was settled by prehistoric humans. There is no evidence of prehistoric human presence on St. Paul Island, though early human settlements dating as far back as 6500 BP were found on the nearby Aleutian Islands. Okay, so I know I see where I left off at Paleolithic people. All right. We're going to continue indefinitely on prehistoric religion and traditional African ancient religion. We get ready to end today's video. And we're going to, all the fields of science, branches of science, formal sciences, natural sciences, and social sciences, and mathematics, indefinitely, and possibly, if need be, refer back to subjects that that we've already gone over, like dualism and cosmology or something, whatever. Well, I mean, still talking about that daggone stupid Gnostic stuff. The scientists at colleges and universities all over the earth, the globe, the planet. They cannot find the origin of Gnosticism. But you want to talk about the material world, and you want to say demiurge, but you can't find the origin of Gnostic. You can't even, what's Gnostic? You can't find the origin of it. Of it. We don't know of it. And then want to, you know what I'm saying, want to destroy, you know, wildlife and nature. You know, want to mistreat the dogs and the cats. Talking about the material world. Want to destroy the North and South Pole. Trying to encourage transgender, transsexual, based on this so-called Gnostic foolishness. But you can't find the origin of it. But in the process of trying to find the origin of it, what do you find? The Indo-European. You know. So, hey, you know, if need be, we might have to go back. You know, we already know about Jehovah. That's a lie. So if we gotta if it need be, we gotta refer back, then so be it. But you know, gonna be on prehistoric religion, traditional, ancient African religion, indefinitely. Branches of science, formal sciences, natural sciences, social sciences, mathematics included, indefinitely. Now I see where I left off on Paleolithic. We on prehistoric religion, prehistory. So I know where I left off when I clicked over to Paleolithic. Scroll. Wait a minute, this is different. Oh, that's upper Paleolithic. Oh, okay, I know. Oh, there it is. Paleolithic. And I left off at Paleolithic people. So like I said, I'm going to get ready to end today's video. So like I said, we're gonna get ready to end today's video. Again, my name is Eric D. Johnson. I was on BrightShine right here. I live right here in the city of Memphis, in the county Shelby, state of Tennessee. Thank my family, my support for your continued encouragement, support. Thank my Lord and Savior Jesus Christ, Son of God, for all the blessings and guidance provides myself as well as all of us with. Continue to pray about natural disasters and continue to pray about wars being fought. Continue to pray for guidance and and support, because can't make it without my Lord and Savior Jesus Christ. And see, that's a good thing about prehistoric religion. We know, it ain't no guess that there was some kind of belief in the higher power, all the way back. Not in the lower Paleolithic, not in the middle Paleolithic. It may have been because burial and the ritual in the middle. Yeah, but like the sign. I'm just repeating, but it might be speculation about the middle Paleolithic. You know what I'm saying? Because of burial and ritual. You know what I'm saying? But they know we can say that in the upper Paleolithic, and when they talk about animism and shamanism, about spirits and things, about burial and ritual in the upper Paleolithic, and then there was some possible mention of ancestor worship, and then when you get from the Paleolithic, you know you came into the Neolithic. Then they started talking about polytheism, some kind of belief in a higher power. You know what I'm saying? The supreme beings, higher power, higher powers. You know, some kind of belief in some kind of, you know, believe in something, you know, that was greater than Homo, greater than us as humans. So we know that, you know, that there ain't no ifs, ands, or buts on that there was during the Paleolithic, the Stone Age. So we can have some reassurance on this. So, you know, I thank my Lord and Savior Jesus Christ, Son of God, for all the blessings and the guidance He provides all with. And so, like I said, I'm gonna get ready to end today's video, and gonna come back on my next video. I'm gonna pick up right where we left off and everything. You know, just try to, you know, and I just want to say this, you know, try to maintain a positive, you know, try to maintain a positive, try to maintain positive thoughts, you know, and because, you know, we seeing things on the news, you know, and then based on what we see on the news, then we know we have an opinion, you know, but still, in your everyday life, man, just try to maintain some positive thoughts, and you know, and not get caught up in things, you know, in issues and stuff, and let your judgment be influenced by something that you just saw on, like, the news, or something you heard on the radio that, you know, that can trigger, you know. But just try to maintain a positive, you know, and don't try to sink down to a negative level, and, you know, just try to maintain a positive, you know, and try to, you know, act on it, on something positive. And so, you know, like, I can just say, for example, I go watch TV or something, like just right now. You know, as soon as I end my video, you know, today is Sunday, got football highlights, and still got Sunday night football, and, you know, you got baseball, this baseball season, then you got soccer, then you got football, Champions League, Premier League. You know, it's always something you can, you know, and then you got WWE, and then you just got movies, you know. And then, you know, I thank my Lord and Savior Jesus Christ just to be alive, just to be able to sit here and do what I'm doing, which is I'm sitting in my own house doing something positive, nothing negative, doing something positive. And so, maintain a positive, you know, and so, you know, think positive thoughts, and positive things gonna result. So just try to stay positive, man. You know, just try to stay positive. Don't go negative. Try to stay positive. Don't be a pessimist. You know, be an optimist. You know, it's always a rainbow. You know what I'm saying? You gotta think positive, man. You gotta get out of this pessimistic view, like it's gonna be a big glacier, you know, the climate. It's gonna be
some big glacier freezing and we ain't got nothing to look forward to. And all, man, you been watching too many movies, man. Look, try to stay positive, man, and you know, and think positive. Be an optimist. Have positive views. You know, work towards something. And so, come back on my next video. And so, you take care of yourself. And, you know, like I said, stay positive. You know, like I said, you know, then I be listening to the radio. And even though, you know, I still try to stay positive. Yeah, I do. I still try to, you know, I'm positive, man. You know, it just, despite what other people do, or, you know, I'm still doing something positive, you know. Because I ain't trying to do like they do, you know, make whack music or anything like that, you know. Because, you know, some people do things for negative reasons. That's being negative, you know. That's being negative. Making whack music, you know. But me, I'm trying to maintain, you know, be positive, you know what I'm saying? I'm trying to steal and cheat other, you know. Try to have positive thoughts and positive things gonna result. So you take care of yourself. Wish each and every one of you the very best.